Hello, this is Andy from the Engineers Academy, and in this video we're going to look at how we can use a software package in order to run some AC simulations. And what we're going to do is we're going to do this in order to replicate some of the results that we've already generated for our RLC circuits. Now the software that we're going to be using is free to students, and I'm going to provide some information underneath this video as to how you can acquire the software. Now the software that we're going to be using is called Capture CIS Lite. And once you've downloaded and installed this software, you'll be able to access it through your Start menu. And the provider of the software is called Cadence. So underneath Cadence, the program that you want to open is Capture CIS Lite. So once the software is open, the first thing that we need to do is to create a new project, because inside that project we're going to have a design and then we're going to have a simulation file. I'm just going to call this Demo 3. And the other thing that you'll need to do is specify the location of where you want that project to be saved. And that can be anywhere on your PC. We have various other different options, and these are the types of project that we're going to create. It's really important that you click the top one, PSpice Analog or Mixed AD. And what that will do is pair your design with the simulation. When you click OK, you'll get another dialog box which asks you if you want to create a project based on an existing project or create a blank project. And we're going to create a blank project and start from scratch. Okay, so the first thing that I'm going to do is to add my components to the page. And we're going to add the components using, in the top menu here, Place and PSpice Components. The reason we're using PSpice Components is because the simulator that we're going to use is called PSpice. Now you'll notice on this menu that we have capacitors, inductors, resistors and so on, which we're going to include in our circuit. But the first thing that we're going to add is our source. So if we scroll down to Source, and we're going to add an AC voltage source. So we go to Voltage Source, AC, and it will provide us with a source. We left click to add that to the page, and then we go back to select our next component, Place. Now the second component I'm going to get from PSpice Components is my capacitor. And you'll notice that at the moment it's placing the capacitor horizontally. Now I'm going to rotate that so it places it vertically, and all I do to do that is right click on the symbol and click on Rotate. And then I can place my capacitor. I can then go back to get my next component, which this one's going to be a resistor, PSpice Component, Resistor. Again, I'm going to rotate this through 90 degrees, right click Rotate. And finally, I need my inductor. So Place, PSpice Component, Inductor, Rotate, and I'm going to place my inductor in line with my resistor. Now we're ready to connect all of our components together, and over on the right hand side we have these quick links, and what we're looking for is this one here that says Place Wire. Alternatively, we can go to the menu we were using previously, click on Place and select Wire. We need a wire that goes from our voltage source to our resistor. We need a wire that goes from our voltage source to our inductor. We need a wire between our resistor and our inductor. And we need wires to connect our capacitor in parallel. Now the last thing that we're going to need before we can run any simulations is a ground for this circuit. And once again we can either go to the right hand menu, Place Ground, or we can go Place and select Ground from there. We'll just keep the default value. And I'm going to place my ground here. We do need a wire to attach that to our circuit, so once again we can select the wire, left click on the ground and left click on the circuit. Now what you'll notice is that there's default values for each of these components. Now I want to edit those values, so I'm going to click on the arrow up here, which is Select, because I want to select the components individually. and I'm going to click where it says 1 volt AC. Now, I don't want 1 volt AC. In this demonstration, I'm going to use 120 volts. So I'm just going to change that to 120 VAC and click OK. Now, I could also change the name of this. If I wanted to call this V3 instead of V1, then I could just double click on the label and change the value there to the name that I prefer. But I'll leave this as V1 for the purpose of this demonstration. Now I have a capacitor here. At the moment it's 1 nanofarad and I want to use 65 microfarads. So I'm going to double click and instead of 1N I'm going to put 65, and the symbol that we use for micro in this package is U. Normally we would use the Greek letter mu, but here I'm going to use U. We could alternatively put this as a farad value, 0.000065, or we can use the U to represent micro. My resistor, I'm going to use a 2.5 ohm resistor, so I click on the value, 2.5, OK. Once again, I could change the label from R1 to R2 if I preferred. And my inductor at the moment is 10 microhenries, but I'm going to change that to 25 millihenries. So 25, and we use M for milli. I must remember to delete the U. Then I can click OK. So all of my values are assigned. Now what I'm going to do is I'm going to do something called a frequency sweep. And what the frequency sweep's going to do is it's going to input different values of frequency for our supply here. So we're going to run this all the way from 1 Hertz all the way up to 200 Hertz. And what we're trying to find, first of all, is our resonant frequency, and then we're going to calculate our Q factor. Now the important thing about the resonant frequency is at the resonant frequency, the supply current is going to be at its lowest. And I'll show you how we can determine this in a moment. But in order to set up our frequency sweep response, I need to do the following. I need to go back to the top menu and I need to click on PSpice, which is our simulation software. And I need to set up a new simulation profile. Again, I can name this. I'm going to call it Demo 3 again to be consistent. And then I'm going to click Create. And what we get is the following box here. There's lots of different options on the left-hand side, but we're only going to make changes in this analysis section. Now the type of analysis, as I mentioned there, is a sweep response. So underneath analysis type, I need to change that to AC sweep/noise. And then on the top right-hand corner, we need to specify the frequencies that we want to sweep between. Now I'm going to do a linear sweep. And I'm going to run the frequency sweep between the frequencies of 1 Hertz and 200 Hertz. Now the important thing here is we can't start at a frequency of 0. If we set a frequency of 0 here, then we're going to get an error. A frequency of 0 is 0 cycles per second, and that wouldn't represent an AC supply, so we must start at 1. Now underneath that we have total points, and that's basically how many data points we want between 1 and 200, and I'm going to go for 2000. That would be roughly 10 every hertz. You can always play around with this and see what gives you the best results. I want sufficient data points to generate a decent number of results. I click Apply, I click OK, and my profile's set. And so the last thing I need to do is to click Play here, Run Spice. Alternatively, I can click on PSpice and there is an option to run in there. So I'm going to run my simulation. And what you'll notice in the bottom menu is PSpice is opened automatically. So I'm going to click on that. And now I can interpret my results. The first thing I'm going to do is I'm going to look at those supply currents at all of those different frequencies. So along the bottom here, we've got frequencies running from 0 Hertz all the way up to 240 Hertz. And I'm going to plot the supply current across those frequencies. Now the symbols are relatively small, but over here we can see a symbol that says Add Trace. Alternatively, what we can do is we can click Trace, Add Trace. And down the left we'll have a list of all of the things we can plot. We'll notice I, open brackets, is currents, V, open brackets, is voltages, and the list will continue further down. But we're plotting the current of the supply. So what I'm looking for is I, open brackets, V1. Now the reason why it's I, open brackets, V1 is because V1 is the name of our supply. If you chose to rename that supply, then it would be I, open brackets, and then whatever you chose to name that supply. All I need to do then is click OK. And what we can see here is the variation of supply currents at different frequencies. Now, as I mentioned, the resonant frequency is the point where the supply current is at a minimum. So we know that we're looking somewhere down here. But what I want to do is to zoom in on that section. I want a closer look at that area. So what I'm actually going to do is I'm going to rerun my simulation with a new profile, now that I know my resonant frequency is around 120 Hz, and I'm going to run it between 100 and 140 Hz. So I'm going to go back to my Design tab, down here. I'm going to go PSpice, Edit Simulation Profile. And this time I'm going to run, as I mentioned, between 100 Hz and 140 Hz. I don't need as many data points now, let's go for 100. Apply, OK, and then rerun the simulation here. Now when I go back to PSpice, I can replot that supply frequency. So this time, trace, add, current across the supply, so I, V1. OK. And now I can hone in and see these values much more easily. So what we can see here is we have a frequency of 120 Hz up to a frequency of 125 Hz, and the lowest point there is just below 125 Hz. So around 124.5 Hz. Now I actually ran these calculations manually and I found that the resonant frequency was 124 Hz to the nearest whole number. So we know that we've been able to replicate those results. Now the other thing that we can do here is we can find the value of that supply current by tracking left. And here we have 1 amp. So each of these increments are 0.2 amps, 0.2, 0.4, 0.6, 0.8. So what we can see here is that we have a current just below 0.8 amps. Now in actual fact, what you can do is hover over these points, and in this window at the bottom, it will tell you the exact values. Because I've tried to maximize the graph on the screen here, I've had to make this very small. But when you're using this on your own PC and you hover over, it will tell you the exact values. So it will say X equals 124, Y equals, and it will give you an exact value here. I'm going to assume that that's around 0.78 because here we have 0.6, here we have 0.8, 0.7, so I'm going to say around 0.78 for the supply current at resonance. But in order to calculate the Q factor, we also need to know the capacitor current at that frequency. So what we can do is we can click on Trace, Add Trace. We're looking for I, and we're looking for the current across our capacitor this time, so IC1. Click on that, click OK, and it will add that trace to our diagram, and we see it here on our graph. So our resonant frequency, we said, was 124 Hz or 124.5 Hz, which is somewhere around here, and we can see by tracking upwards that the current through the capacitor at that frequency is just above 6. Just take a little bit of care here because our scale has changed. We have 6, 6.57, 7.58. It's modified the scale to accommodate the larger current. But if we go over here to our 124 Hz, then we have a current between 6 and 6.5, and that looks to be around 6.1. Now, if we wanted to calculate our Q factor at resonance, all we would need to do is divide the 6.1 by the 0.78, and running that through the calculator gives us a Q factor at resonance of 7.8. Now, as I mentioned, I have done this as hand calculations, and the value that I calculated for the Q factor at resonance was 7.8. So our simulation supports the calculation that I did earlier. Now, one big advantage of this method is that if we want to change any values within our circuit, we can change those values and rerun the simulation between the same parameters. So let's say, for example, I wanted to change my capacitor to 60 microfarads. And I wanted to change my resistor to 25 ohms. All I would need to do is edit my profile, so PSpice, edit simulation profile, choose the frequencies that I want to run between. This time I'll run between 1 and 200, and we'll just have 200 data points. Apply, OK, and then hit play. Now when I return to my simulation, I can replot the current across my voltage source. So trace, add IV1, and what I can determine from the new plot is my new resonant frequency, this time around 92 Hz. So we can easily make adjustments and retest to produce the results. As mentioned at the start of this video, I'm going to provide details on how you can obtain this software for free as a student, and then you can begin running some of these simulations for yourself.